Hello and welcome. In this problem, a block of copper heated to 1000 Kelvin is dropped into a chamber, a rigid chamber containing 1 meter cube of air. The conditions are given to us. And we are asked to find the equilibrium temperature. Obviously, the chamber is assumed to be insulated, completely insulated, so there is internal heat exchange between copper and air. We are also asked to find the entropy generated because of thermal friction. Okay, so this problem is interesting because you notice that not only the final temperature is unknown, but also its final pressure is unknown. On top of that, we got to understand that copper is a solid, and we can use the SL model for copper, and for air we have been asked to use the IG model for air. Okay, so let's get started with a suitable app. So we go to the closed branch, obviously, and follow the non-mixing process. We go to generic branch, and non-mixing process is the correct one, where the two subsystems are not allowed to mix. And the model we pick is the multi-model because one of the subsystems has to be handled with SL model and one with IG model. So going back to the PowerPoint, let's make sure we decide on which is what state. So in the beginning, these are my BA and BB states. So we'll call copper state to be state 1 and air state to be state 2. And then we'll carry that to state 3 and 4. In other words, we'll go from state 1 and 2 going to 3 and 4. But we have to make sure that 1 goes to 3 and 2 goes to 4. So that's a little bit tricky. We have to be careful about that. Okay, so state 1, we have SL model, and we should select copper. So we go find copper here. Okay, and the temperature is given as 1000 Kelvin. What else we know? 5 kg of copper. Of course, we could declare some of this variable in the I/O panel if we wanted to do a parametric study. So notice that we don't need to know the pressure of the copper, although we understand it will be 100 kPa because air is at 100 kPa, because SL model doesn't need pressure to calculate energy or entropy. Okay, now state 2, we have to switch to the IG model. So let's go to IG model, and air is the default fluid already. 100 kPa is given to us. Temperature is 300 Kelvin. And I think the volume is supplied to be 1 meter cube. So this is the easy part. State 1 and 2, we know the energy and entropy of each of the states. So what is state 3? State 3 is the final state of copper. So again, we go back to SL model and select copper here. Of course, the mass of copper block cannot change, so it will be equals M1. And question is, what else do we know? If you think about it, we don't know the final pressure, final temperature. So at this point, we have to just leave everything unknown here. So we don't know the energy or entropy of state 3. For state 4, we know a few things because the volume of the tank. First, let's select the model, IG model. State 4 is the final state of air. We know that the volume cannot change, so it must be volume at state 2. That was our air volume, 1 meter cube. And of course, the mass cannot change, so mass will be same as M2. So these are the only information that we do know. We also know that finally, state 4 will have the same temperature as state 3. We know that for sure. The question is, obviously T3 is not known. Can we determine what T3 is? Notice that, T4 is not, T3 is equal to T4. So T4 is the final temperature, or desired answer. P4 is also a desired answer. So two unknowns right here. So you go to the process panel and try to take advantage, set up the process. and we will take advantage of the energy equation and mass equation to get to the answer. So state 1 and 2 are our beginning states. 1 is copper, 1 is air, and 3 is copper, and 4 are copper and air. So this is correctly loaded. And also we know there is no boundary work because there is no change in volume of the entire system and there is no heat transfer. So if we do that, it's very difficult to figure out the answer. So in this particular case, you can figure, because there is too much iteration involved, easier way to solve this problem is to go back and guess a final temperature. We know that the temperature has to be between 1000 Kelvin and 300 Kelvin. So let's say we take a wild guess. We say, okay, 1000 Kelvin and 300 Kelvin. So, 1300. So maybe the answer is, 600 Kelvin. So you do a calculate based on that. What happens is that if you do a super calculate, it will update everything. And you can go to the process panel and see what Q we got. So had we assumed a 600 Kelvin final temperature, it says that Q equals minus 513, which means heat is getting lost. So obviously, to get 500 Kelvin, to get 600 Kelvin as the final temperature, some heat has to be lost. Ideal answer would be what? Q should be 0. So this is how we bracket it. So a guess of 600 Kelvin brings us negative. So let's assume the final temperature is higher than that, so that there is no heat loss is necessary for equilibrium. So let's say the final temperature is, 800 Kelvin. With that, if I calculate and super calculate, go back to the process panel, yeah, Q is positive, and it's not too much positive, only 55. So obviously 800 is a better answer than 600 Kelvin. And likewise, you can go and iterate like this, and you can soon find that if the answer is close to 780, then the Q become almost close to 0. So in other words, this is our final solution. You can refine it even further if you want, but this is good enough. So we already found what is the final temperature here by guess and check, essentially. And notice that the final pressure would be in state 4. So we have found the final pressure and final temperature, and the process panel, of course, the entropy generation because of thermal friction, heat transfer, internal heat transfer between copper and air. So this is a fairly complicated problem, but you see how the iterative nature of TESTapp works. The information flows from state panel to process panel, and if you have a cycle panel, it can go forward like that. So guess and check is really easy with the use of the super calculate button.